Problem 18.8. Write the mechanism of acid-catalyzed cleavage of T-butyl cyclohexyl ether to yield cyclohexanol and 2-methylpropene. So first draw the structures. The reactant is ether, so draw oxygen. One side is T-butyl, the other side is cyclohexyl. And product is a alcohol, cyclohexanol, and E is a alkene double bond because it's a propene, methylpropene. Okay, so in acid condition, ether will be protonated. First step, draw acid, chlorine, bromine. Okay, X represents chlorine or bromine as an acid. So the proton, the oxygen lone pair electron goes to proton, and bond between hydrogen chlorine or bromine bond break. So what you get is a anion. All right. At the same time, the ether is protonated. Oxygen has 3 bonds, so it's positive charge. All right. So the next step, 2 possible ways. One is the anion serve as a nucleophile to attack the smaller side. That will be SN2 mechanism. In that case, this bond break, and the left side give you alcohol, the right side give you a alkyl halides. All right, so remember, if it's SN2, it will attack on the smaller side. On the other hand, if the molecule, the ether, contains a T-butyl group, like here, the reaction next step always SN1 instead of SN2. SN1, then the oxygen carbon bond break, this bond will break, give you a T-butyl cation. Okay, remember T-butyl cation is relatively stable, so it can be easily formed. And therefore, if it's SN1, you have a T-butyl group, then you draw arrows shown here to show the bond between carbon oxygen, the bond between this bond break. All right, the 2 oxygens goes to 2 electrons goes to oxygen. So what you get is a T-butyl cation, and the right side is an alcohol, and that's the one of the product. Okay, so what happens to the cation? 2 possible ways. Okay, one is the anion serve as a nucleophile, attack carbocation, give you a substituted product, and that's SN1 mechanism. You form carbocation and followed by nucleophilic addition, give you a substituted reaction. Another way is this anion also can serve as a base to deprotonate one of the hydrogen, and a double bond will be formed. Okay, so in fact, the question tells you the product is a double bond, and that indicates it's an elimination reaction. So for clarity, I redraw this carbocation here. So again, this is a carbon cation, and CH3, we draw CH2 with another hydrogen here, just to show what happens in E2 elimination. So now here the anion serves as a base, deprotonate this hydrogen, and the bond between hydrogen carbon break give to the carbon that forms a double bond. So that's the E1 elimination. So give you this product, so another product. Problem 18.10. What product would you expect from Claisen rearrangement of 2-butynyl-phenyl ether? So butynyl-phenyl ether is also called allyl ether. The right side 3 carbon with a double bond is called allyl group. Allyl group is a 3 carbon with a double bond. All right, this carbon is called allylic carbon. So that's the allylic carbon. Okay, 3 carbons. And the right side benzene is called aryl. All right. Now for the Claisen rearrangement, the benzene only this double bond, one double bond participate in the reaction. So you can consider this as a vinyl. So double bond is called a vinyl group. All right. And therefore, you can think about this ether as allyl vinyl ether. All right, the Claisen rearrangement only involves these 6 atoms. So if you count 1, 2, 3, 4, 5, 6. Allele, venial, 6 atoms participate in the Claisen rearrangement. Okay, this one does not participate in the reaction. No matter how much you add, how many, so you can add. They don't participate in the reaction. You may also add another benzene ring, but they don't participate in the reaction. Only in this system, okay, allele, venial system, ether, they participate in the reaction of the Claisen rearrangement. So for clarity, we redraw this structure to show here this allele group and the venial all together, 6-membered ring. All right, the 6 members carbon. And for Claisen rearrangement, which is also called a pericyclic reaction, the mechanism is just electron movement, and so we can just push all the electrons. So here is the mechanism, and we can push the electrons, all right, to show this pi bond goes to here to form, is going to form a new bond, and then this pi bond move to here to form a new double bond, and this single bond will break, goes to here. So you just push electrons one by one in Claisen rearrangement. Okay. Now some people may ask, can you draw the opposite way? So this pi bond go here to form a bond, and this pi bond move to here. Yes, you can. You will get the same results. All right. So let me clear. Okay. So through a transition state. So this is called a transition state, in which this new bond is about to form, but not yet, and this pi bond is about to break. Will go to here to form a bond, but not form yet. So it's everything happens simultaneously. So this is a new bond that old bond is about to break, and this is about to form. Everything happens at the same time. Okay, so remember, transition state is an instant between reactants product. It's not something you can isolate. Okay, so here is the product. A bond, a new bond is formed. Okay, it from this pi bond. Remember, it moved to here. So that's the new bond, and then this pi bond break. So now you become a single bond, and it goes to here, and you form a double bond. And this bond break. All right, go. So now here you don't have any bond. You go to here, form a double bond. All right. So this is the product come from Claisen rearrangement. Now, in allele ether, there's one more step. Okay, this is because we start with a benzene ring. Here, it's not a benzene. It loses aromaticity. There's a mechanism to restore aromaticity. There's a hydrogen here. Okay, this hydrogen can shift to this oxygen, and then this double bond, pi bond, move to here. And that will give you a new product. You notice that now you get aromatic compound. So restore aromaticity, but now the hydrogen moves to here. In fact, you form the phenol. All right, and this is the product for Claisen rearrangement when you have allele ether. Okay, Claisen rearrangement. If you don't have this benzene ring, then this will be the product. Okay, for normal allele venial ether Claisen rearrangement. Okay, the last step. This step is also very common. The hydrogen shift is called keto-enol. So if you have a keto, okay, a CO double bond, this is called a keto form. All right, and a double bond with hydroxy. Okay, this is called the enol form. All right, keto-enol form are isomers. They are isomers because one of the hydrogen of this carbon adjacent to carbonyl carbon is called alpha carbon. If alpha carbon has a hydrogen, this hydrogen can shift to oxygen, give you enol form. So keto enol form. So let me erase this. Okay. So here you have carbon, hydrogen. All right. So alpha carbon hydrogen can shift to oxygen, give you enol form. All right. This isomization is very common. In fact, to enol is not favorable in most cases. If you have enol, it most cases go back to keto. All right. So go back to keto. But in this case, if you can see here, this is keto form, and here is enol form. A double bond with hydroxy is enol form. But in this case, enol form is more stable. The reason is it has a aromatic system. It forms aromatic. In the keto form, it doesn't have aromatic system, and therefore the isomization goes to the right side, give you this product. In the last slide, the mechanism was drawn using line bond structure. Some people prefer carbon hydrogens added. So here is the same mechanism, but with carbon hydrogens all added in the system. So they are equivalent, same. It's just probably more clear to some people. Some people ask about alpha and beta carbons. In a carbonyl compound, the carbon adjacent to carbonyl group is called alpha carbon. So this is alpha, the next one will be beta, and this is gamma, and here is delta. Okay, so sometimes a carbonyl compound may have more than one alpha and beta. So for example, acetone. So in this molecule, this carbon and this carbon are both alpha. You have two alpha. On the other hand, formaldehyde does not have any alpha or beta carbons. Now, these carbonyl compounds can called gamma delta unsaturated because there's a double bond on gamma and delta carbons. Okay, now gamma delta unsaturated ketone can be produced by a rearrangement from allyl vinyl ether. Note that this is allyl, this is a vinyl. All right, so the rearrangement happens when you push electrons. So pi bond go here, just like we did, okay, in the Claisen rearrangement. So when you do that, you will get this gamma delta unsaturated ketone. And the rearrangement is called sigma tropic rearrangement. Now, when the R and R prime forms a benzene ring here, in other words, instead of allyl vinyl ether, if it's allyl aryl ether, so this is a benzene ring, then this rearrangement becomes Claisen rearrangement. So here what you get is now you only have two double bonds, and then this hydrogen shift to the oxygen that give you phenol, as we shown in the last question. So this rearrangement is called Claisen rearrangement. So Claisen rearrangement is a special case for sigma tropic rearrangement. Sigma tropic is for allyl vinyl ether, as we shown here. Okay, and Claisen rearrangement is when the vinyl group becomes a benzene ring. So then you have one more step, the hydrogen shift, resume aromaticity. Now, alpha carbon is very important in organic chemistry. It has many properties. Okay, for example, this alpha hydrogen, so note that this is carbonyl, so this is alpha carbon, and this is alpha hydrogen. So alpha hydrogen is acidic, okay? It can be deprotonated, For example, if you use hydroxide, it will deprotonate this alpha hydrogen, and it will give you a enonate. So this carbon becomes negative charged lone pair electron. This enonate, you can draw resonance structure. So the lone pair electron go here, pi bond go to oxygen. So you have a resonance structure that the lone pair electron goes to oxygen, and oxygen has higher electronegativity, and therefore it stabilizes the negative charge. So enolate is relatively stable because two resonance form can delocalize the negative charge onto a carbon and oxygen, can make enolate stable. Okay, so because enolate is relatively stable, so the hydrogen, alpha hydrogen, is acidic. Okay, and so in fact, when you protonate this enolate, okay, when this oxygen is protonated, and that gives you the eno form. Okay, remember we mentioned in the last slide, and this is eno. All right, and this is keto. So keto, eno. All right, so this is called keto-eno tautomization. This is the mechanism for the alpha hydrogen shift, as we discussed in the Claisen rearrangement. So again, alpha carbon has many important properties. One is the hydrogen is acidic, can be deprotonated, and that opens up many chemical reactions. One example is when you treat bromine, the alpha hydrogen can be replaced by bromine. Okay, so there's two chapters in this organic book. Chapter 21, 22 are both about alpha carbon reactions. So the alpha carbon reactivity in carbonyl compounds is an important topic. Unfortunately, we won't have time in this class to discuss this important topic. So, but if you like organic chemistry, I suggest you read textbook chapter 21, 22, and that will have detailed discussion of alpha carbon reactions.